G'day everyone. Today we're going to continue our discussion of the Dirac equation, and we're going to talk about free particle solutions, which will lead us to understanding the spin space or the Dirac space a little bit better. It'll lead us to the explanation of the Dirac sea. Then we're going to do minimal coupling to the electromagnetic field, which will lead us to the result that the electron G factor equals 2. In other words, that the coupling to magnetism is twice as strong as classically predicted for the spin. And the last thing we'll do is look at conservation of angular momentum. So let's get started by looking at the free particle solutions with no field. Last time we wrote the Dirac equation in a Schrödinger-like form with the matrices alpha and beta being 4x4 matrices. In the standard representation, we can write alpha, which is a 4x4 matrix, and I'll write it the same way I did last time, which is writing it as a 2x2 matrix of 2x2 matrices. So the sigma matrices are the Pauli matrices, 2x2, and when I write 0, I mean a 0 matrix, which is a 2x2 matrix. And similarly, I would write beta is equal to 1 minus 1. And the 1 here is the 2x2 identity matrix. Minus 1 means the negative of the 2x2 identity matrix. And the zeros are 2x2 zero matrices. So this is always... we often write these Dirac matrices as 2x2 matrices in this way. It just makes life a little bit easier for us. So in that representation, I would write I d psi by dt is equal to alpha dot p is now going to be, each one of these alpha i's is going to come with sigma I. So I can just write this one as 0 sigma 0 dot p plus 1 0 0 minus 1 times m times psi. And then I can take that dot product explicitly, which would give me so sigma dot p is also a 2x2 matrix. And when I write m here, I mean m times the 2x2 identity matrix, which is the diagonal mm. And putting all of that together, if I have a free particle with a particular energy, I do feel like I've written this particular line about 1 million times in this course so far. I usually roll with a plus I, don't I? P dot R minus ET. So that will be, for a free particle, that's the ansatz I want, but then there'll also be a 4x4 matrix to go with it. So I substitute that in, and I'm going to have, I'm going to make this even more explicit. I want to write psi equals some 4x4 matrix, some column 4 vector psi naught. So that's some column vector that's independent of space and time, because I want all of the space and time to be encapsulated by that exponential factor. So plugging that in, I will get E psi naught is equal to, I'll just add up these two matrices, M sigma dot P minus M times psi naught. Now sigma dot P is kind of not very complicated, but we can make this thing even simpler by just letting P be in the Z direction. So without loss of generality, we can let P be in the Z direction, or in other words, choose the Z direction such that it is aligned with the momentum. And then I know what sigma dot P is. So sigma dot P will be just sigma in the Z direction times P. And sigma Z is the easiest of the Pauling matrices to remember. And I will get E psi naught is equal to. Now I want to write this as a 4x4 matrix. So M is M times the identity matrix. Sigma dot P is sigma Z times P. So that's sigma Z is 1 minus 1, if you remember. So this will be P minus P. Sigma dot P again. And then minus M is minus M times the identity matrix. And now I have an eigenvalue equation for psi naught, where psi naught is just some column vector. And so a few things to note about it. Firstly, if we look at I'm going to change the colors here for a second. If we look at the shape of this matrix, we can see that the column here, the first column, and the first row are coupled together, and the first and the third columns are coupled together, and the second and the fourth columns are also coupled together. So you can see that you can sort of separate this matrix into like two matrices just by swapping row 2 and 3 and column 2 and 3, right? Interchanging the rows. But you can also just plug it into Mathematica and solve it. Either way, delete that. We have an eigenvalue equation for the matrix, and it will lead to four solutions because of a 4x4 matrix. We'll have E is going to be plus or minus EP. And remember, EP is defined as the positive square root, just like we had before, of P squared plus M squared. And each solution is doubly degenerate. So if we look at the eigenstates, so just rearranging that a little bit, sorry about that. So the energies eigenvalues are E equals plus or minus EP. So for the E equals plus EP eigenstates, we're going to find that we have the eigenstates look like this. 1, 0, I'm not normalizing these, I'm just writing them out. So like I said, the first and the third column are sort of coupled together. And the other solution is where the second and the fourth column are coupled together. So that's the two eigenstates for psi naught. And maybe instead of and there, I should have an or. No, and is good. And the other eigenstate is E equals minus EP, which is also doubly degenerate, and has solutions psi naught equals minus P over M plus EP 0, 1, 0 and 0 P over M plus EP 0, 1. So you can see that there is in all of these solutions, there's a part which is the large part, which is the 1. And for small values of momentum, then EP is sort of close to M or minus M. And so you end up with a small component in the top for the negative energy state and a small component in the bottom two slots for the positive energy states. So I said that this is spin space, and now I'm going to kind of prove that. So consider the operator sigma, which is a vector operator, and it's a diagonal a diagonal spin like that. All right, so it's a 4x4 matrix, which I represent as a 2x2 matrix. So this is a 4x4 version of the spin projection operator sigma. So you can show that for the free Hamiltonian, for free particle Hamiltonian that we've been using, that sigma dot p commutes with it, and it also commutes with p itself. And that means that another good quantum number can be formed from the helicity operator. The helicity operator is defined as sigma z, where z means in the direction of p, right? Because we chose that, which is the same as sigma dot p. This is vector operator over the magnitude p, right? So sigma dot p, so it's the sigma in the direction of p. In our case, where we've decided that we're going to have p in the z direction anyway, we can just write this as sigma z 0, 0. All right? So it's going to define positive and negative helicity. So for states which are spin up, that's going to correspond to positive helicity now. So this operator will project out the spin from our wave functions. And because we've chosen z to be in the direction of the momentum, it means that if we've got momentum in this direction, and that's also the z direction now, but if the spin is aligned with that, then that's called positive helicity. Right, so we can think of that spin as, using the right hand rule, you're thinking about the spin like so. Whereas for negative helicity, you've got the momentum in this direction, and the spin will be in the other direction. Like so. And that's negative helicity. Okay, so that kind of explains why it's called spin space, because you can see that the different terms, the different points, the different numbers in the column vector, either the upper component or the lower components, they correspond to what we normally call spin. And you can also take the non-relativistic limit of these guys, and you can see in the non-relativistic limit when this lower component here is going to be small for the top one. So in the non-relativistic, P over M plus EP is going to be a small number. And so it will have a large upper component and a small lower component. So it kind of touches where we were with the Dirac equation. The next thing I want to just touch on is this free particle spectrum, where we've seen that for the free particle, E equals plus or minus the square root of P squared plus M squared. And let's actually map that out. So what we can draw is energy versus magnitude of the momentum here, P. And for P equals 0, E equals plus or minus M. And what happens as we go away from that is you get this asymptotic approaching like this. So for the positive side, it looks like that. And for the negative side, it looks like that. So we've got this hyperbolic energy spectrum. And you can see that for every momentum, if I'm at, say, this momentum here, then I've got a positive energy solution and a negative energy solution. And each level, so every point here is doubly degenerate. Because of the helicity or spin, right? So for this point here, there can be spin aligned like that or anti-aligned like this. So that's 2 points effectively at each of these. Yeah. Here the spin could be aligned or anti-aligned. That's what it looks like in momentum space. What about if we just go back to real space? So in real space, the picture would look something like this, where I've compressed all of the momenta, and now we have a Dirac spectrum for every position x. And so for every position x, at every point in space, we have an infinite set of positive and negative energy states corresponding to different momenta and positive and negative energies. And so if you imagine you've got an electron represented here by a little dot, this guy here, and you say, okay, what's going to happen to that electron? Well, the question is, what stops this electron from then just kind of falling down into some of the many, not filled spaces here? And in fact, it can keep going. It could increase its momentum and get a more negative energy. So it could just accelerate away to even lower momenta and keep falling down like so. So the question is, what stops that electron from falling? And Dirac had a quite surprising solution to that. He said, well, these are fermions, so they can't be in the same place at once. He said, all negative energy states are filled. That means that there's an electron in all of these spaces. Yeah, so all of these ones are filled. Electrons everywhere here. And in fact, if they're all filled, then this is prevented because 2 electrons cannot be in the same space. And then he even gives us an extra idea. What is a positron then? A positron, so if all of these are negative energy states are filled, all of these are filled with electrons to stop the real electrons from falling down to minus infinity, then a positron is a hole in the Dirac sea. So if you imagine like some light comes along and you've got, or maybe I just use the same diagram. You've got some blue light. It comes in from the side here and it excites one of these electrons from here up to there. Then the electron is formed in, so this is kind of like making, an excitation in a semiconductor, right? So you've got a hole that's left behind where an electron was. It has all of the properties of an electron, but because it's a hole, it's got the opposite charge. And so it will look like an electron, but with a positive charge. And so a positron is now explained, and when they were found a little bit later, it was kind of indication of this bizarre theory that you've got this negative infinite sea of electrons. And it turns out you can formulate a nice quantum electrodynamics. In quantum field theory, you can formulate this nicely so that this infinity of a Dirac sea is kind of removable, and you don't end up with infinite energy. But for the purposes of gravity, it's a real problem, this Dirac sea, because one way or another, the fact that you've got this infinite mass of electrons at every point in space is going to come back and bite you. So this is kind of like the fundamental reason, if you like, why there's no good way of putting quantum field theory and gravity together. Okay, next thing we want to do is look at electromagnetic interactions. In minimal coupling, we would then write that the momentum is now got to be written in the kind of covariant momentum way, just like we did with the Klein-Gordon equation. And for the same reasons, because this way the total derivative or the covariant derivative, and if we make that change at the same time as we make the change to the phase of the wave function, then we have the gauge invariance that we need for our theory. So let's consider an electron in a pure magnetic field. And we'll make the field homogeneous and isotropic. And we're going to solve our equation now just by writing something like this. So we'll write this as a two-component vector, phi chi, where phi and chi are spinors themselves. So this just follows our normal notation of writing the 4x4 matrix as a 2x2 matrix, or writing a 4-column vector in this case as a 2-column vector, where each of the elements in the 2-column vector are themselves another 2-column vector, which are the spinors. So we substitute this into our Dirac equation, and we're going to furthermore assume that it's constant energy. So we'll have for a homogeneous magnetic field, we will have E psi is equal to, and actually let me write that using our new notation, phi chi equals, so expanding the alpha dot p out, you get something like what we did before, and we can even compress this a little bit further by adding these two matrices together. So I'll replace these directly by m and minus m. It's just like what we did before. So far I haven't made any assumptions except that there's constant energy. And then I will take the mass of the other side, and I basically have two equations here, right? One for phi and one for chi. And so let me write out the one for chi. So I've got E chi is equal to sigma dot P minus EA. So this is just writing out the lower equation here, times phi minus M chi. Or I could write chi is equal to sigma dot P minus EA. So this is for a constant energy times phi all over E plus M. Okay. By the way, this is another way of generating the non-relativistic spectrum. You just write, or just the solution for the free particle as well. This is quite general so far. This I haven't made any assumptions. Now what I'm going to do is I'm going to take this chi, I'm going to substitute into the top formula. So that means that I can write E phi equals M phi plus sigma dot P minus EA chi. That's the top equation. And now I substitute this into here, and I will get plus sigma dot P minus EA times sigma dot P minus EA all over M plus E times phi. And so now I've just got an equation for phi, which is a spinor. And now what I'm going to do is I'm going to take the non-relativistic limit. E is approximately equal to M. And that means that M minus E I would write as approximately equal to minus epsilon, where epsilon is like the non-relativistic energy without the rest mass. So if I go over here, I've got E minus M phi is equal to, now I need to make this, I need to solve this complicated thing here, which is sigma dot P minus EA squared. Okay, now that we've got this non-relativistic equation, we need to expand out the complicated sigma dot P bit. And we will use the identity, which you all should know, or at least be able to prove. So the identity we need is sigma dot A, where A is some vector, sigma dot B, and B is another vector, equals A dot B plus I sigma dot A cross B. So you can prove that yourselves. That's the identity that we use. And so now I'll expand out my non-relativistic equation. Now be careful here, because the momentum is not, we're not in a momentum eigenstate, right? There's a magnetic field, so our electron is going around in a circle or in a helix. So that P, we're going to have to write it as minus I grad. We're not going to be able to just say it's a momentum. And so this cross product is not going to disappear, because it's the I grad is going to act all the way on the A and on the phi. So let's do some color coding here. Blue, sure, why not? We'll start with this term here. So once you've reduced it to this form, we now need to actually make that cross product. And in order to do the cross product, we really just have to look at the cross terms, because when we do A cross A, we're going to get 0. And when we do grad cross grad, you're also going to get 0, because that grad is actually applied to the phi on the right. So let's make this expansion. We're going to have the minus I times I is 1. We'll take the E outside, E here, sigma dot And then we're going to have grad cross A and A cross grad applied to phi. And let me write that out kind of explicitly just so that we are completely clear on it. This is like curl of A phi. And this one is A cross grad phi. And so we can use our usual rules that you can find in the electrodynamics textbooks for doing this expansion. And the first one will be grad cross A times phi minus A cross grad phi. And the second term, we can just leave it as it is. And we see that these last two terms cancel out. And so we're just left with E sigma dot grad cross A phi. But of course, the curl of A is just the magnetic field B, so we'd just write this as E sigma dot B phi, which is looking pretty good. We also probably want to do a similar thing for the other term, and so I guess I will pick another color again. Purple is always brilliant. So we'll take the purple one here, this guy, and work out what that one does. So P minus EA squared. I need to pick a gauge now, and so I'm just going to use the kind of curly gauge that we use sometimes. Use A equals 1/2 of B cross R. Yeah, so that, you know, the curl of A is equal to B. And so if I use that gauge, then P minus EA squared is equal to P minus E over 2 B cross R squared. And that is approximately the same as P squared minus 2 of these, which is E P dot B cross R, plus terms of order like B squared or A squared, which we don't really need to worry about because that's like A squared on C squared, right? So we just let those ones go. And this is equal to, we can use the rules of the triple product here to rearrange this as minus E. So you can do cyclic permutations. So we can do B dot R cross P. You can always do cyclic permutations of a triple product. And R cross P, you'll recognize, is L, the orbital angular momentum. Right, so putting all of that together, therefore, we will have E phi is equal to P squared over 2M minus E over 2M B dot L plus, if we go back to this one, this is sigma dot B and E, and I've lost a factor of a minus sign somewhere here, and I'm not 100% sure right now where that is. Oh, it's just, I should have taken minus E outside here. Okay, so let's just do that now quickly. So that should have been a minus E taken outside. Minus E, minus E, minus E, minus E. There we go. Saved by the bell. Let's go back to this one. And so we've got minus E over 2m sigma dot B. Times phi, which we can write as P squared over 2m phi minus mu B L plus 2s dot B, where mu B is equal to E. I'll put my H bars and C's back in, as I like to do every now and again. E H bar 2MC. And S is equal to 1/2 of sigma, as usual. And so, yeah, we get this nice equation, and there it is. There's the G factor, G equals 2. Right here. And so we've recovered the electron G factor. Just before we kind of leave this topic a little bit, I want to just express the Pauli equation. So the Pauli equation, so that's the correct equation for spin half particles in the non-relativistic limit. And we get this directly from the Dirac equation, and it's easy to follow all the steps to get to that. And the extra thing that we should notice is that there's kind of a plus beta, plus m phi here. That's from the beta m term. And the Dirac equation gives us this bit, but that just is kind of like a rescaling of the energy, just like what we have above. So usually we don't include the rest mass in the non-relativistic limit, but if we do include the rest mass, then we should be including it here. And so this is the correct equation, the correct wave equation for spin half particles. The last thing we want to talk about today is angular momentum. And let me write out our equation one more time. And now what I want to do is I want to have the central potential. So the potential is just a function of r, not a function of the direction of r. So for the 3D Schrödinger equation, the orbital angular momentum is a conserved quantity, and that's because the operator L commutes with p squared, and that works for the and p squared is the kinetic energy term, right? It also commutes with the central potential term V of r. For the Dirac Hamiltonian, though, we have a slight problem. Each component of L does not commute with alpha dot p. So we're going to just show this, and the way I'll do that is by doing this. So we have alpha L P L, where L is just an index here. No meaning. It's just this is L goes from 1, 2, 3, and there's an implied summation because the indices are repeated. And same with L, I can write it's R cross P, so I can write this as epsilon I J K R J P K, where again, because we have repeated indices J and K in this equation, we have a summation over J and K equal 1, 2, 3. putting that together, I can then take out this factor ijk and the alpha L, and I will have PL RJ. That's the part that might not commute. PL always commutes with PK. And alpha is in its spin space rather than in real space, so that one's always going to commute as well. So this is using the same tricks that we used before about the commutation relationships in one of the previous videos. So if we take this epsilon ijk and we'll make the commutation now, PLRJ is minus I delta LJ. And so then we can write that as minus I epsilon ijk. L is now equal to J for the non-zero terms. So we can write alpha J PK, and that's nothing but minus I alpha cross P in the I direction. So what does all that mean? So that's something that you should probably get used to doing as well. So what does that mean? It means that alpha dot P does not commute with L. In fact, we get this relationship here, not equal to 0. So orbital angular momentum does not commute with the Dirac Hamiltonian. Okay, what about spin? We came up with an operator for spin already before. S equals 1/2 of sigma, where sigma was, and again, remember this is a 4x4 matrix being written as a 2x2 matrix. Clearly, we've got beta sigma rather, is equal to 0. What about alpha and sigma? So let's take, by the way, that's a vector operator. What about alpha? And I would actually encourage you now to pause the video and attempt to do this yourself. So have a pause. I'm going to keep going because there'll be a time shift now. You're going to pause and I'm going to be writing here, and you can restart when you're done. So I'm just expanding this out in full. Hopefully you guys were able to do this yourselves. Seriously, if you haven't done it, now's the time. Pause. And we can expand this out. So the first term is sigma I, sigma j, 0, minus, and the reverse term, sigma j, sigma I, sigma j, sigma I, 0, which is zero times the commutator sigma I, sigma j, commutator sigma I, sigma j, 0, which is equal to 2I epsilon ijk 0 sigma k 0, or we would write this as 2I epsilon ijk alpha k. So that's the commutation of alpha I and sigma j. And so if we wanted to know what alpha dot p does, well, again, good time to pause the video. Remember, alpha I, pi has the repeated index I, so there's an implied summation here. And because epsilon ijk is antisymmetric, we can rotate those indices as well, and we will get 2I alpha cross P in the J direction. Right. So spin also doesn't commute with alpha dot P. But if I put all of that together and I write J equals L plus S, then I can write L plus 1/2 sigma alpha dot P is equal to, it's I alpha cross P minus, get back up here, where's my angular momentum, minus I alpha cross P. So the spin part and the orbital angular momentum part exactly cancel each other out, and so you get 0. And so therefore total angular momentum is conserved. Okay, and I think that's probably a good place to stop for today. We have done a few things. We looked at the free particle, we looked at the Dirac C, and then we did some minimal coupling to lead to G equals 2, and then we've done angular momentum conservation. So that's probably a good place to stop for now.